Okay, thanks everyone for the patience. We got everything to work now. Uh, okay, so we'll start with the plenary lecture. So it's my pleasure to introduce Dr. Manish Gupta. Manish Gupta is the director of Google DeepMind India, where I'm fortunate to be a part of. So before joining Google, Manish was leading the research centers for Xerox and IBM in India. And Manish is very well known for his technical work. In particular, he led the team that developed the system software for the Blue Gene supercomputer while he was at IBM. Manish is the recipient of many awards. He's a fellow of the ACM and INAE, the Indian National Association of Engineers, and he also received the Distinguished Alumnus Award from IIT Delhi. So without any further delay, I hand the mic over to Manish, and he'll tell us about the transformative power of AI. Thanks.
Thanks, Praneet. Again, thanks to the Ashoka team for this opportunity. A lot of people have remarked that, so I'll talk about the transformative power of AI, but one thing that AI still hasn't solved is these projector issues, internet access issues. Someday we'll solve those problems too. So so I represent an organization within Google called Google DeepMind, where our mission is to build AI responsibly to benefit humanity. And one really kind of a powerful, in some sense, demonstrator, right, of that mission this year was this Nobel Prize in Chemistry that in fact went to two of our I can say researchers, one of them being the founder of DeepMind, Demis Hassabis and John Jumper. So in fact, I do have a connection to this protein folding problem because one of the machines that I worked on when I was at IBM Research was called Blue Gene. In fact, the name Blue Gene, Blue was the IBM, Big Blue. Gene was not the genes, but the genes, right? As in our in those 23 as in those genes, right, that control everything in our body. So the in fact, one of the motivating applications for Blue Gene was this protein folding problem, which has been really like a grand challenge in this field. So in those days, again, there used to be this approach. Again, people were trying with ab initio molecular dynamics, basically simulate the laws of physics and simulate the movement of all these atoms, molecules, and so on, and through which try to uncover the unique shape that each sequence of that amino acid folds into, which gives the protein its distinctive properties. There used to be this biannual contest called CASP, where structures of newly discovered proteins were used to test software that was used to predict. In those days, it used to take about a PhD to uncover the structure of a single protein. So it required usually about 5 years of research work. And in those competitions, again, there used to be basically software, all these entries used to be ranked. And I think it was 2017 when this RL-based method from AlphaFold did quite well. And 2 years later, in the same competition, it did so well in terms of coming up with the structure of these unknown proteins, or previously whose structure was not known, that basically the community said the problem seems to be now effectively solved. And in fact, then AlphaFold was made openly available, and the team worked on, again, predicting the structure of all 200 million proteins known to humankind. So you can say that something equivalent to about 1 billion PhD years, right? Because each protein used to take about 5 years. So for 200 million proteins, you needed something like 1 billion PhD years to uncover the structure. And again, I wouldn't claim that it accurately would have predicted all of them. In fact, there are scientists who are pointing out problems that still exist, but still, it was very close to like accelerating something like 1 billion PhD years through, again, AI-based methods. So that shows again, and it's not just unique to protein folding. I mean, if you look at weather forecasting, so many problems, material design, and so on, um, fusion. So the uh, research community is excited that they feel. So today, fusion is still not a practical reality in terms of being able to generate clean energy. Uh, if it was feasible, it would help us generate very clean energy, because what you get as a result of fusion are these helium, so there's no reactive, no toxic material being produced and so on. But today, it takes more energy to create that fusion reaction than the energy that you get out. So that break-even point has still not been reached. And what scientists believe is that through, again, AI-based uh, methods through which you control the flow of plasma and so on, that is how you'll get there. Again, it's not done yet. Um, Weather forecasting, there are already AI-based methods which are actually now beating the traditional physics-based simulations. Um, some of these systems that have come out of Google Deepmind and Google Research, GenCast, in fact, many of them are now being open sourced. You're finding that uh, basically for things like medium range weather forecasting, these models run something like over 100,000 times faster than the traditional physics-based codes, and they are actually producing more accurate forecasts for medium range as well, which is considered a fairly hard problem in weather forecasting. So we are seeing, again, a lot of very impressive advances in, in science in particular. Uh, but today, again, I won't talk too much more about AI for science. I'll start with kind of a very brief historical perspective, in particular for deep learning. Uh, uh, then talk about the current trend of foundation models. Uh, and if you go back 10 years ago and you asked AI experts, what would AI be used for? Most experts would have said it will be used to kind of automate a lot of the mundane tasks that we do as humans. Creativity will remain this uniquely human endeavor. And what you see is, again, now AI helping create beautiful pieces of art, images, music, and so on, while we are still doing a lot of the mundane work ourselves. So, uh, so somehow advances in this field have caught even the experts by surprise. So I'll talk a little bit about some of that. Then a topic very close to my heart, inclusive AI. How do we develop AI in a manner that benefits everyone? Because we still see a big gap between these AI models' capabilities, for instance, on languages like English. On problems arising in the Western context, you find, again, AI models working extremely well. But on many problems arising in the Indian context, you still don't see them working as well. So I'll talk about some of those kinds of problems, um, which in particular our team in Bangalore has been doing a fair amount of work, and then some open challenges and takeaways. So, so first to talk about deep learning. So in fact, it is very interesting that AI has been this very broad field. Uh, there were so many different approaches to AI. And the one that caught on, I remember when I was in your shoes, many of the students, when I was doing my undergraduate, I remember like expert systems was this big thing that our professors were teaching us about in that AI course. Uh, uh, all of those approaches fell by the wayside, and one particular subset of that field, machine learning, really took off, where you make the machines learn from data. Again, within machine learning, if you see, there were so many different approaches. Uh, SVMs were hot, support vector machines, and so on. And there was this artificial neural networks was one approach, which was one of many approaches to machine learning. And for many, many years, in fact, the community had given up that these artificial neural networks don't work. But, but starting around 2011, when it made that comeback, it hasn't looked back. So that one approach in deep learning kind of has really taken off. Um, and so what we find is increasingly, we are finding that within AI, increasingly narrow set of kind of approaches are becoming dominant, but the applicability of these has been increasing. I mean, in early days of AI, there were relatively few problems that you would apply AI to. Today, practically any problem that you think of, AI is being used to uh, help solve that problem. So it's very, very interesting and surprising in hindsight that an increasingly such a narrow uh, set of approaches. In fact, the transformer architecture that I'll briefly touch upon is helping with such a broad class of problems. So, uh, so deep learning, I think anybody who's not familiar with how deep learning works, so I'm sure everybody would have heard the term deep learning. Uh, how many of you at least know basically how deep learning works? Show of hands. See, most of you, but there are still a few hands that have not come up. So maybe I'll just spend a few minutes. Uh, so, so deep learning is loosely inspired by how the human brain works. And from your biology lessons, you might remember that there are these neurons and those connections. So the equivalent of neurons are these very simple and represented through these dots in this figure, are these very simple mathematical units organized in layers that together work to solve these problems. And, and in fact, uh, so, so these mathematical units would be doing computations very, very simple. Something like take the input, multiply it by a coefficient, a weight, add an offset term, pass on the output, right, to the next layer. Or take all the inputs, take the maximum value, pass it on to the next layer. So they do as simple computations as that. And yet, when you have a collection of these neurons and then stack them up, uh, uh, there is, in fact, they can do some very, very interesting thing. In fact, there's a universal approximation theorem that says any computable function can be approximated even by a two-layer deep network. Uh, uh, so that's theory, right? And there's a famous saying that in theory, theory and practice are the same. In practice, they're different. So how does it work, right? In practice, theoretically, yes, you can approximate any computable function. Uh, so so early years, 1980s, again, there were some promising kind of results that Geoffrey Hinton and others showed, but then even Jan LeCun showed this whole digitization of uh, all these. I think US Postal Service was using this automated system to identify the zip code, which was using that deep learning solution. But the community had pretty much given up. But 2011, when this uh, uh, deep learning system made a comeback, okay, before that, uh, what does it mean, right, for this network to be trained to solve a problem? What that means is, so in solving this problem, right, what you're doing is, let's say you're feeding this network an image of this cat, and you want the network to answer, what does this image represent? Is it a cat or a dog or a human, aeroplane, car, and so on, right? Object identification or image classification problem. Uh, so what you do is you have these mathematical units working on those pixel. Oops, what happened? Pixel values. Did I lose the Zoom connection? Okay. So, so what you're doing is you're doing all those computations uh, on those pixel values. And at the end, you will do some kind of a softmax computation, some max computation, right? And come up with a number. And if you have, let's say, different kinds of objects, right, which are encoded. Let's say 0 represents a cat, 1 represents a dog, 2 represents human, and so on. Uh, so the network produces an answer. Uh, and the way these are trained is, again, using sound mathematical principles, right? That you set up something like a loss function. So what you do is you start with label data. where you already have certain images where you know what was the dominant object in that image. And you look at the output of this neural network, and the difference between the output and the true value, you set it up as a loss function, and then you minimize the loss function with respect to these parameters. So you choose the parameters such that the loss function, right, which is the error, is minimized. And choosing those weights, choosing those parameters, right? So things like the weight that you would multiply that input by and the offset term that you will add and so on, that is called training the network. So what the research community saw was these networks could be trained to solve a very diverse set of problems. They could do this image classification. Soon after, again, that entry in that MNIST competition, which was based on the deep learning approach, which led to a drop in the error rate by close to 10%. I mean, every year, again, there used to be like maybe fraction of a percent drop in error rate. And deep learning based entry led to close to a 10% drop. That made people sit up and pay attention. Soon thereafter, uh, speech recognition problem, right? You take an audio signal, identify what words are being spoken. There was an entire research community that had been building these automatic speech recognition systems by like cascading language model, acoustic model, and so on. And out came a deep learning based approach where you just did end-to-end learning. You trained the network with millions of these samples of audio with labeled data, with where you knew what words were uttered. And now, if you tried this network on new speech data, you started to get better accuracy than a lot of the traditional uh, uh, automatic speech recognition based model. Similar things started happening with machine translation. Uh, and even this complex version of this original problem, where given an image, you're describing how coming up with a caption for that image, the way a human might describe that image. Um, and so, so what was very, again, interesting is that over this previous decade, maybe the decade starting from 2011, what you started to see systematically is on a broad range of problems, deep learning systems started becoming the state-of-the-art way of solving those problems. They started overtaking other machine learning-based methods. Uh, so, so what was unsatisfying about this, right? What was still missing? There were two things that were still deeply unsatisfying about this approach. One was that it required too much of labeled data. For all of these problems, again, typically these neural networks were trained on millions of labeled data points. So, so that was one problem. The other problem was that for every new problem, you had to train a new network from scratch. Now, the combination of that makes it kind of not very practical. If for every problem, you now have to train a new network from scratch and you need millions of annotations, uh, it becomes impractical to solve many, many problems using this approach. So that was then tackled with this new paradigm, foundation model, which again, interestingly, is like a subset of the deep learning based methods, which is now becoming the dominant paradigm within the field of deep learning itself. Uh, and one major research breakthrough that enabled uh, these foundation models to emerge was this transformer model, transformer architecture, uh, famously presented in this NeurIPS paper, 2017 NeurIPS paper, Attention is All You Need. And just to maybe illustrate how transformer, again in very simple terms, how transformer worked, uh, and also another issue that was tackled, which was of dealing with having to label all the data. So, so the researchers came up with methods known as self-supervised learning, where you find the label within the data itself. So just to illustrate how self-supervision and transformer architecture worked. Uh, what uh, uh, for this model BERT that you might think of as perhaps one of the first foundation models. It wasn't, I mean, the term wasn't even coined then, but one of the first kind of really powerful NLP models, which was again uh, presented by Google researchers in 2018. What the team developing BERT did was they took this open text from sources like Wikipedia, digital books, and so on. And what they did was they masked out roughly 15% of the words and then started training this model, BERT model, to predict those missing words. So I don't know about you, reminds me of this fill in the blanks exercise my school teachers would give me when I was learning English. Later I learned Tamil. All language teachers were always giving this fill in the blanks exercise. And through that exercise, and so BERT was given this fill in the blanks exercise. And to predict those missing words, it used the transformer architecture. So now to predict the word, let's say born here, you're looking at a context window, words in this uh, context window. And you're using the transformer architecture, you're like trying to pay attention uh, to different words. And the transformer architecture, as it explores kind of uh, uh, the, the significance of these different words, it automatically figures out a way of paying more attention to words like Obama, 1961, Hawaii, which have more bearing on the prediction of this word born. So, so through this, as this BERT got good at predicting those masked out words, similar to how kind of when our teacher gave this exercise, they were testing A, our ability to understand the language, and B, reason about things from the surrounding context. So, so in this process of again figuring out those missing words, BERT was forced to learn the nuances of the language as well as build certain representations about the world, because of which it was able to now not just predict those missing words, but come up with effective solutions to many, many natural language processing problems, including things like sentiment analysis, which was very commonly used. Let's say somebody is posting things on comments on social media. Brands are very interested in this person saying good things or bad things about my brand, or things like question answering. Given a piece of text, can you answer questions based on that text? Or summarization. Can you take a piece of text and summarize it? So on a lot of these different NLP tasks, BERT-based methods started doing quite well. Uh, uh, that's a good question. I don't know. Some expert may know the answer. Does it? You do. Yeah. So this was, yeah. So if you fast forward to maybe about 2.5 years ago, when Google developed this large language model called Palm, it wasn't kind of released externally because of concerns that it may be misused. Uh, but there was this very interesting exercise that the Palm, that the researchers at Google did in comparing. So this was a 540 billion parameter model. Now remember, I mean, that original diagram that I showed with deep learning that had maybe a few hundred parameters, right, in that picture. Uh, the kind of modern networks that you have, they have hundreds of billions, now even exceeding a trillion parameters. So Palm 540 billion parameter model, what the team did was they compared the performance of this model on 58 different tasks, benchmarking tasks, with the best known model for each of those 58 tasks. So again, remember, we are going from this era where you had to train a separate model, right? So in this earlier era, you had to train a separate neural network, right, for each of those tasks. Uh, and now you're trying to compare the performance of this one model against the best known model for each of those 58 tasks. And this chart shows the relative performance, right, in terms of quality of Palm versus the state of the art, whatever custom model. And you can see that, yeah, these orangish colored bars show that, yes, the custom trained model did better. But you can see that on a vast majority of tasks, the Palm based model started doing better than the previously state of the art custom trained model. So it is, again, this kind of a foundational capabilities that led the Stanford researchers to coin the term foundation models. And this trend emerged that increasingly, instead of having to train separate networks for each problem, you start with a foundation model, and either out of the box, it gives you good performance, or you fine tune that model to come up with a more effective solution to that problem. The other thing that the researchers were surprised to see is that it wasn't just solving some of these classical NLP, natural language processing problems. It was even showing some ability to solve mathematical puzzles like this. Let's say there's this simple puzzle. John takes care of 10 dogs. Each dog takes half an hour a day to walk. How many, sorry, this is the question. Uh, how many hours a week does John spend taking care of dogs? So what they saw was that if you simply gave this question and asked the model to answer, right, it would usually get it wrong. However, if you did something called chain of thought prompting, if you prompted the model with similar problems and also showed the model how to solve that problem, uh, and the similar problem didn't have to be syntactically very similar to this. You can see that something like this problem, Sean has 5 toys. For Christmas, he got 2 toys each, and so on. How many toys does he have now? So this is not syntactically very close to this. It's just using similar mathematical principles as this problem. So what they saw was, if you prompted the network with examples of problems that required similar reasoning, and also not just gave the answer, showed step by step how to solve that problem. Again, reminds me of our math teacher always saying, don't just solve the problem, show me step by step how you have solved the problem. So if you showed this model step by step how to solve the problem, and again, when posing a new problem and asking the network, hey, think step by step, they were surprised that these models were even solving some of these mathematical uh, puzzles. So this is chain of thought prompting. And again, a lot of, again, reasoning, I wouldn't say is a solved problem. This is a very active area of research, but there's a lot of work being done building upon this chain of thought uh, way of tackling problems. The other interesting thing was, it wasn't, this foundation model approach wasn't only working for languages, for text. It was starting to work for other modalities too. So for instance, medical images. A lot of the early work in medical imaging, let's say you have um, X-ray images of lung. You want to figure out, is this a case of lung cancer or not? Or mammography images, and you want to see, is this a case of breast cancer or not? Um, Earlier approaches were typically based on supervised learning, that again, you had to take often millions of these images, get expert radiologists, doctors to annotate those images, and then you trained models on those annotated images to come up with an AI model. Now, what our researchers found, that if you now started with unlabeled medical images, but lots of them, started building kind of good representation using, again, self-supervised learning, and then you simply fine-tune those models with fewer examples of those labeled images, they started to see higher quality and more robust models uh, compared to the traditional model. Similar thing was seen with speech data. What Google researchers found was, earlier, it used to take us, like, for any new language, we often needed, like, uh, definitely tens of thousands, often over 100,000 hours of labeled speech data before the model became good at recognizing uh, words spoken in that language. And, and there was a model built using now a few million hours of unlabeled speech. And now, if you fine tune that model with even 1,000 hours of speech data for a given language, we found that this model started to do better, higher quality than a model that was trained using much more, let's say tens of thousands of hours of speech data just for that language. So again, it was very interesting to see uh, this particular foundation model approach take off for so many modalities. Uh, so now we are, again, there are a variety of foundation models from various companies. In fact, Google's hand was forced by OpenAI coming out and releasing ChatGPT, because earlier Google was very concerned about releasing anything based on these foundation models because of concerns about misuse, including bias and all kinds of issues. Uh, but now there are a variety of models. There's GPT-4, there's uh, the model from Anthropic, uh, Cloud, there's Llama model from Meta, and so on. So again, I'll talk more about Gemini, not that I want to advertise, but because that's the model that I have more familiarity with and access to more of the results on Gemini. So, so, so showing, right, some of the capabilities that today's models already have. So I'll start with three capabilities that Gemini 1.5 model showed about a year ago when it was launched, roughly a year ago: multimodality, long context, and agents. But agents, there's been more progress in the most recent launch. So first, multimodality. So while popularly these models are often now referred to as LLMs, large language models, today they are not just processing language, they are processing not just text, they are processing pretty much all modalities. And this is an example uh, uh, of, let's say, a prompt that was given to Gemini 1.5. And you can see that this is a multimodal prompt. There is, so it is asked about a problem, physics problem that's posed to a student as well as the student solution. And the model is asked this question: did the student get the correct answer or not? And if not, where did they make a mistake? And you can see uh, this has a combination of, again, typed text, there's a diagram, there's some handwritten text. And I'll admit this is a cherry-picked example. Gemini 1.5 will not work so beautifully on every such uh, problem that you throw at it. But the fact that it worked on this problem still kind of, I found it very surprising and quite amazing that the model is able to figure out, oh, from this diagram, oh, this is that well-known popular problem of where somebody at the top of a slope, their potential as they ski down, their potential energy has to be converted into the kinetic energy. Maybe all those Resnick and Halliday books that we used to study while preparing for IIT entrance exam and so on. It also had seen those, and it plugs those equations for potential energy, kinetic energy, is able to solve that and point out the error that the student has made. Now, imagine again a capability like this really means that this whole goal of personalized learning, right, that we have, that's been like a almost like a holy grail, it now seems within reach. There is still actually a lot more to learning than simply getting the answer. So in fact, the team working on a personalized tutor at Google DeepMind, it's working on a personalized tutor called Hypatia. And in fact, one of the key approaches that they're taking is, even when the model knows the answer, you don't want to just give the student that answer. You want to give them hints that will help them get to the answer themselves. But again, some impressive capability that these models have. Another one that I'll show is this long context window, right? So remember in that Obama was born example, the context windows in earlier times used to be fairly small. Word, how much was it? Praneet, do you know, was it 64 tokens or that? Oh, Bert? But there used to be, I mean, these 64 words or 128 words that you look at. Uh, and, and in fact, there was interesting work done by some of our uh, team members, of which Praneeth is part of, this tree former methodology, uh, which, anyways, I'll talk more about that later. But today, these context windows are becoming very large. So in fact, Gemini announced initially a 1 million and then a 2 million token context window. And to give you an idea, roughly 1 million token means that it would capture something like of the order of 700,000 words of English, right? So not just one textbook, they're like a dozen textbooks or an entire maybe uh, even a small encyclopedia, right? You could capture through that context window. So that is the number of, again, tokens that the model is looking at before making that next prediction, that next token prediction. So, uh, so these models have become, are supporting such a large context window, or something like an hour of video, a million tokens. You can feed as part of your prompt an entire 1 hour long video and now a 2 hour long video for 2 million tokens and ask the model questions about that video. So the model hasn't been trained on that video, but that video can be part of the input. So to showcase that, let me play this and see if the audio plays. No, the audio is not coming. Okay, so maybe instead of trying to figure that out,
44-minute Buster Keaton
I
film,
don't know if this
which comes out to over 600,000 tokens. In Google AI Studio, we uploaded the video and asked, find the moment when a piece of paper is removed from the person's pocket and tell me some key information on it with the time code. This screen capture is sped up, and this timer shows exactly how long it took to process each prompt. And keep in mind that processing times will vary. The model gave us this response, explaining that the piece of paper is a pawn ticket from Goldman and Company pawnbrokers with the date and cost. And it gave us this time code 1201. When we pulled up that time code, we found it was correct. The model had found the exact moment the piece of paper is removed from the person's pocket, and it extracted text accurately. Next, we gave it this drawing of a scene we were thinking of and asked, what is the time code when this happens? This is an example of a multimodal prompt, where we combine text and image in our input. The model returned this time code, 1534. We pulled that up and found that it was the correct scene. Like all generative models, responses vary and won't always be perfect. But notice how we didn't have to explain what was happening in the drawing. Simple drawings like this are a good way to test if the model can find something based on just a few abstract details, like it did here. These are just a couple examples of what's possible with a context window of up to 1 million multimodal tokens in Gemini 1.5 Pro.
The other thing which is coming is this agentic capability. And okay, let me just do this.
Fun drawing. Is it Albert Einstein?
Yeah, what did he do around this time?
Let me just play it some.
Try to guess this famous figure.
That's a fun drawing. Is it Albert Einstein?
Yeah, what did he do around this time?
In 1905, Albert Einstein published his groundbreaking theory of special relativity. Do you want another hint for your drawing?
Does this remind you of any of his work?
Yes, that drawing reminds me of his photoelectric effect paper, which also won him the Nobel Prize in 1921.
Okay. Do you know who this is?
Is this a new famous figure? This makes me think of gravity and Isaac Newton.
Did he share anything with that first guy I showed you?
Both Isaac Newton and Albert Einstein were physicists who revolutionized our understanding of the universe.
Thanks, Gemini.
So today, you have, again, we have gone beyond a kind of just conversational agents, which you have to type. So ChatGPT had launched, there was a ChatGPT voice version, audio version that was launched. Likewise, Google launched Gemini Live. What I showed is the Astra that Google has launched with right now trusted testers. This is not generally available, but it is available to a select set of users where you can see that these interactions are happening not just through voice, but also the system, right? The agent is able to see kind of the environment, right? So there, it's like a video interaction which is happening with this AI model. Uh, I'll, I think I'll skip. So more recently, there has been this Gemini 2.5. Oops. Why is it stuck? I'll skip that. Uh, that Gemini 2.0. I think I've shown you enough of these demos. So the other thing which is happening is, as I mentioned, AI models are being used to basically help with tasks that require creativity. Uh, and you see, again, people asking these models to write some poem, uh, create an image, create videos, and so on. And to show some examples, uh, text to image models. So what I'd shown from the first generation of deep learning models was that given an image, it could come up with a caption for that image, how a description of that image. Now, the reverse direction also works quite well. You can give a very, very detailed description of what you want, and then the model will generate a very high quality image. So you can see again how these are a very detailed set of instructions, and the model has very faithfully adhered to those instructions and created a fairly high quality image. And these are again examples of images that have all been synthetically generated by the Imagine 3 model from Google. Um, and a simple extension of that has also led to this VO model for video generation, which internally first uses Imagine 3 to generate that initial image, and then you start generating additional frames. And again, this is an example. So right now, these video generation models are relatively rudimentary, but again, you can see them over time becoming quite powerful. That give it a prompt, and it is able to generate this cute video. Another like interesting kind of a domain within whatever art would be music. And again, I'll show maybe one example of this AI-based model being used together with musicians to generate new kinds of music. So let me just play this.
Put this right back into the music AI tool, the same. Boom, 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 boom. What happens if Haiti meets Brazil? Dude, I have no clue what's about to be spread out. This is what excites me. As a hip hop producer, we dug in the crates. We playing these vinyls, and the part where there's no vocal, we pull it, we sample it, and we create an entire song around that. So
Okay, cut it off. So again, these are ways in which now AI models can actually help uh, artists create more interesting art. Uh, and and now turning to the next topic that I wanted to cover, which is inclusive AI. How do we make sure these kinds of model capabilities work for everyone, right? Not just the privileged few. So I'll cover three broad themes very quickly. One is uh, how do you make these models perform well in a broader set of languages? So for Google, again, these models get used as part of Google search, which is a very important tool to provide people access to information. So we think of this as democratizing that access to information, that you and I, we are the lucky ones, that privileged ones for whom information is available at our fingertips because we understand English. How do you make, let's say, down this road, let's say there's a laborer in Panipat whose daughter wants access to that same information, but in Haryanvi, how do you empower her with that same level of information that you and I kind of take for granted? Uh, so I'll talk about that challenge. Agriculture, you look at something like close to over 40% of the households in India are dependent on agriculture for their livelihood. And yet, uh, again, rampant problems. Farmers find it very hard to get access to loans, reasonably priced crop insurance. Crop yields in India tend to be extremely low compared to kind of what has already been shown possible in many other countries. So a lot of areas through which you can positively impact farmers' lives, which so far, right, hasn't really uh, kind of made it into the real world. And then efficiency, because as these generative AI models have taken off, two things that we have seen going up is one is the energy consumption of these data centers. So increasingly in news stories, right, you keep hearing about all of these companies now signing deals with nuclear uh, energy providers and so on. The overall energy consumption of the world is going up quite substantially because of, again, these generative AI workloads as they, and if let's say today, magically, uh, the 1.4 billion Indians or whatever, let's say maybe amongst, if let's say the young kids, 2-year-olds aren't using these AI models, let's say a billion, close to a billion Indians started using these AI models. Today, there isn't enough hardware, right, in the world to actually run those models. So how do you make them also more energy efficient, right? So, so of course, the other thing that I mentioned, which has been going up, is the Nvidia stock price. So nothing wrong with Nvidia stock price. I have also now bought that stock. I mean, some time back. But energy consumption, you definitely want to reduce. So a lot of work, in fact, that Praneeth and team have been doing in this area. So first on languages. Uh, so this was a paper that our team presented at the ACL conference last year, where we came up with this benchmark called Indic GenBench with uh, lots of different kinds of tasks that you might want to do, like answering questions posed in a different language or asking for summarization of a piece of text in different languages and so on. And we saw a pretty substantial gap between pretty much all models, including Google's own, on English. So these stars, blue stars show the performance of these models on, let's say, Palm L model on English, and compared to when you look at the performance on Indic languages. So here we covered 29 Indian languages in this benchmark set. So we saw a pretty substantial gap. Uh, so uh, our goal was to now start closing that gap. So the effort within our team is called Morni, uh, which is again a continuation of, which is an expansion of a previous effort called Mural. So Partha Talukdar, who leads that effort, and his team had previously built a model called Mural, which at that time provided the largest coverage of Indian languages. It covered 16 Indian languages and English. And the Mural embeddings were made freely available. So many researchers use Mural. When I challenged Partha to make sure we handle all 22 scheduled languages, he in fact came back and told me you aren't being ambitious enough. So he gave me this data point from one of the language surveys done in India many years ago, about a decade, more than a decade ago, which, which shows that there are 60 Indian languages which have over 1 million speakers each, and there are 125 languages which have over 1 lakh speakers each. And so he said, I want to build a model that covers, that understands each and every one of those 125 languages. But that's easier said than done, because he also told me, by the way, 72 out of these 125 languages, when we started this work, were zero corpus languages. That means there was zero known digital data on those languages. So this is kind of very both like disappointing that you have languages spoken by millions of people or hundreds of thousands of people with no digital presence. And in a way, it's not surprising because if you think about Hindi, which is spoken by roughly 10% of the world's population, given India's large population, uh, close to 10% of the world's population actually speaks Hindi. Guess what percentage of the open web content is in Hindi? Any guesses? 1%? Good guess. 0.5%? A better guess? 0.1% is the correct answer. I mean, that's the closest. If you approximate it, 0.1% of the world's web content, openly accessible web content, is in Hindi, uh, even when 10%, right? Almost 10% of the world's population speaks Hindi. So, so, so most of these Indian languages are low resource languages. So there's a lot of, again, challenges in how you build models that will, because there's no hope, right, of amassing as much data as you have for English. There's no hope that you'll get as much digital data for each of these languages as you have for English. So you need other ways of tackling that problem. The other challenge was that the same language is spoken in so many different ways. Uh, so I'll skip this video, but it, again, the same problems, the same question, Pragati Madan kaise jaएं? How does one go to Pragati Madan? Spoken in so many different ways. So in fact, in India, there's this saying, "Kos kos pe badle pani, char kos par vani," that every whatever few kilometers, the taste of water changes, and then 4 times that distance, the language changes in India. So that saying, in fact, inspired this project called Vani that we launched jointly with ISC Bangalore to capture the speech landscape of India. So here, oh, 5 minutes. Okay, thanks. So here, instead of uh, taking this language-centric approach, we took a region-centric approach uh, of collecting data, where we kind of have our vendors go and collect this data, and we don't tell the people donating that data what language to speak. We ask them to answer a few questions and describe an image that's relevant to them, and in their own preferred language, and then tell us what that language is. So we recently made the data from the first phase of that project, covering 80 districts and over 14,000 hours of audio data. We made it freely available. So it's available to all researchers from this Vani website and also the Government of India's Bhashini site. It covers 59 languages, and 15 of those languages used to be zero corpus languages. So this is the first known digital data for at least 15 of those 59 languages. And again, as we continue this effort, the goal is eventually to collect speech data from each and every one of the 773 districts of India, so that we hopefully capture the full diversity of languages, dialects, accents. So the other technical problem that arises is, yes, you build a model that understands all these Indian languages very well. How do you combine that with the power of a model like Gemini that otherwise has very powerful capabilities, right, that I showed, but doesn't understand Indian languages very well? Is there a way you can combine the best of both worlds? So that approach, again, was developed by a team called CALM, which is a way to automatically compose two language models with cross attention. This was presented at the iClear conference last year. And also, again, there's an open source version of CALM, which is available. And the idea was to basically build a smaller model that understood Indian languages very well and compose it with the Gemini model. So that was the motivation here, was language inclusivity. But you can imagine a similar approach can work even for things like domain-specific models. Let's say you want to build a model for coding problems or clinical problems. Can you kind of build a specialized model for that domain-specific problem and then compose it with a foundation model? So in fact, as we tried this out and as we built these models for assisting with tasks like translation, we were able to, last year, Google released an updated version of the Google Translate uh, product. And in fact, in one shot, it covered 110 new languages, because through this model that we had built, which understood now 1,500 languages, uh, this model was doing a better job on translation than kind of the previously custom trained translate model on many of those languages. And then for about 110 languages, it now started meeting the quality bar that the translate team had. Um, the other issue is, it's not just a question of understanding a language, you also need to understand different cultures. So let's say for a user in Assam, you don't want to just come up with the response in English and simply translate that response in Assamese. Or similarly, you can imagine for Japan, if you just come up with the response in English and translate that into Japanese, you may not have the most appropriate response. Uh, so how do you develop better cultural understanding in these models? So that's the other problem that our team has been working on. And we have seen, again, already through these, uh, especially these multimodal models, that there's a lot of challenges. Lack of diversity, uh, inability to really understand the cultural context. Uh, and while these images look not so bad of Ravana, the person pointed out they have any number of heads other than 10, right? Which is the correct number of heads uh, Ravana was supposed to have. And I'm out of time, so I'll maybe just spend 2 minutes each on these. Uh, Agriculture, what our team has been doing, and we have built the first such model that based on satellite imagery for the entire country, we are able to identify things like farm boundaries uh, and start to identify kind of crops which are being grown and so on. And the idea is to provide the foundational layers of a digital agri stack. Just like mobile payments, right, were revolutionized in India through this Aadhaar stack, which started with first a unique identifier for each human. So in a similar analogous manner, we are giving a unique identifier to each field so that you're able to, for instance, a farmer can now just present information about their farm, the land coordinates, and the bank can, at their fingertips, access enough information about what's happening at the farm level in terms of what the farmer has been growing and so on. They can assess their credit worthiness or suitability of buying, let's say, insurance for cotton crop, because they can verify, is the farmer actually growing cotton if the farmer has come to buy insurance for cotton crop and so on. So that's the idea. And some of the technical challenges involved were that we had to, I mean, there were models like this already available, but we had to push on all of these dimensions. Spatial dimension, that farms in India tend to be much smaller than the farms in countries like the US. Temporal dimension, that you have to detect many of these things at sub-seasonal level, because, I mean, if you are trying to identify the crop, you want to identify it not at the end of the harvesting season, even early on. And spectral, that for during the monsoon season, much of the country is covered by clouds. So you can't have the traditional uh, RGB camera give you the right data. You also need other bands. So how do you kind of use that? And finally, efficiency, I think I'll skip. Praneeth is the resident expert on that. So I would say if you have questions, maybe you can, uh, uh, or if you want more details. But very briefly, one of the things our team developed was these elastic models, where instead of using the same model, all kinds of problems, all kinds of queries, can you make these models elastic? So that if there's a simple problem, you just need a small version of the model. If there's a more complex problem, you need the larger version of the model. So, so the same model, can you train it once and make that model available in different sizes? We first did that for embedding models. That work was Matryoshka representation learning, presented at NeurIPS 2022 or 23. Yeah, one of those. Yeah, time flies. 23. And then that idea was extended to transformers called matformers. This was presented at NeurIPS 2024 recently. And these ideas have also gone into this Gemini models and so on. And then uh, people like Praneeth have done a fair amount of work in looking at these different components of an LLM and looking at speeding up all of these different components. So for instance, the generation of this output is done in an auto-regressive manner, one token at a time. So something called a tandem transformer, where instead of using just the larger model, you use a smaller model in tandem with the larger model, paying attention to the larger model's representation to do this generation. So the smaller model is faster, so the sequential task can be speeded up. Uh, Speeding up this attention through a technique called preformer, where instead of paying that n square penalty, if you have n tokens, uh, instead of paying that n square cost, can you start doing some clustering, use a tree to kind of get to the right cluster and so on. So can you bring down the time complexity from order n square to closer to n log n? And then higher, where you, instead of taking contributions from every uh, other token, can you identify the top k tokens that you need to attend to and only kind of take their contributions? So this technique called higher. So again, through this, we have been improving the efficiency. But finally, I would say there are, oh, I missed that slide. There are still a lot of open challenges. So, I mean, there's problem of efficiency that I've already touched upon. There's problem of hallucination that many of you may be quite aware of. LLMs very confidently generating kind of bad output. Problems are bias. And again, many of these problems like bias have not been studied too much in the non-Western context, where again, our teams have been very active. So many of these, uh, so many of these problems led companies like Google to formulate these AI principles. And I would still say, while we strive to make sure our models conform to these principles and our products conform to these principles, many of these still are unsolved problems. So in fact, I know from Google research and Google DeepMind alone, in the last few years, there have been over 200 papers just covering various methods to help make these models more responsible. But still, there are, again, I think hundreds of PhD theses to be done in just tackling some of these problems. But finally, I'll conclude that AI is already here in a significant manner, impacting every industry, every aspect of how the world is being run. We have seen this rise of foundation models, generative AI models, which are now providing a very powerful starting point for a very broad set of problems. And this is an amazing time. So I'm certainly very envious of all the students in this audience, because you are entering your careers in this time of, again, amazing capabilities. So you pick any problem and you can get a very powerful kind of a starting point, right, to tackle that problem using these foundation models. Uh, and basically the sky is the limit, right, in terms of what you can do with the help of technology, right, to tackle these problems and benefit billions of people. So these are very, very exciting times. So both in terms of new problems being solved, as well as foundational problems with the AI models themselves. So we are at this very interesting point where on one hand, these models have amazing capabilities that they can tackle these problems like protein folding, weather forecasting, and all kinds of generating art, all kinds of whatever, customer support, all kinds of real world problems. On the other hand, these models also have glaring weaknesses, which themselves require further research. So it's just an amazing time to be an AI researcher, an AI practitioner, or whatever, a solution builder, because uh, you can do very, very both interesting and meaningful work. So with that, let me stop. Thank you.
Manish, for the wonderful talk. So any questions?
We'll pass the mic.
Hi, Manish. So we often see that memory is a problem, and there is this concept of catastrophic forgetting when you add new information. So are you like doing any kind of research or have any had any breakthrough in that?
Yeah, I wouldn't say breakthrough. Yes, there has been uh, a lot of work on continual learning, and can you do it in a manner that avoids this problem of catastrophic forgetting? So I do know there have been papers, like there's one of our colleagues, Pradeep Shenoy. He has published a few papers on this problem. There's been a collaboration with Piyush Rai, who's at IIT Kanpur, in this area. And likewise, I also know about of teams based in Google DeepMind in London and New York who have been working on these, as well as external researchers. So this is a very active area of research. Uh, I wouldn't say we have breakthroughs, but yes, some good progress has been made.
Yeah, hello, sir. I just wanted to ask about that video thing. So, was the model explicitly trained in physics drawings, or was it just like trained in the given data and then it just learned it from there?
Yeah, so the model was that Gemini model, right, that you're talking about. It was trained on lots and lots of whatever uh, things like books and so on. And there would have been a lot of those question answers, right? And those images and sample problems and so on that it would have seen. So yeah, it wasn't just trained specifically on pictures. This was just trained on lots
Data.
and lots of openly available data, uh, as well as licensed data, and and not specifically for the physics problems, and it was doing well on those physics problems.
So Manish, going a few years ahead, does one see kind of these foundation models with these big companies like Google, Meta, others, they being the kind of, I guess, suppliers, and then startup companies coming up with their companies which who build applications on top of these foundation models? Is this where we are headed? What's the kind of, what do you think?
Yeah, so definitely there's a lot to be done by startups and others utilizing these foundation models to build solutions, build actual applications that will solve real world problems. Because often companies like Google are not necessarily the best ones, which would focus on that small set of initial customers and come up with that really good solution. So in that sense, that area definitely has a lot to offer. My own belief is that there should also be more work done, because I don't think we have already seen the best way of building these foundation models. So I would love to see more foundational work also being done by academia, by startups, and others in even better ways of building these foundation models. Because if you take inspiration from the human brain, I mean, human brain does it all with roughly, it's estimated about 20 watts of power consumption. And these models are consuming whatever, megawatts uh, of power. So, so we know it can be done more efficiently. So I would love to see continued research in better ways of even building these foundation models.
Hello, so thank you for the talk. You said a lot things about the generative AI foundation models and the amazing things it can do. So, what do you think about these models when they learn uh, about how to control what these models learn, how to align them with what we want, if they are learning what we intend them to, or they are not learning something else? So, and how do you feel about the importance of this kind of research in today's times of Gen AI and
Yeah, yeah. So that's a very important kind of a class of a set of issues, right? Or that you have brought up. So if you go back to that responsible AI, that definitely is uh, how do you uh, a kind of be socially beneficial, avoid creating biases, are built for safety. Because in many cases, right? I mean, if you give, for instance, somebody asks you how to whatever build a bomb through which you can whatever kill lots and lots of people, uh, how do you avoid, right, helping people with those kinds of destructive tasks? Or somebody has a medical question, how do you, and the model isn't very confident about the answer, how do you avoid giving whatever the wrong answer? So So within those, even these responsible AI principles, there are many aspects where that alignment with how you want a model to behave responsibly is important. But alignment itself is a very kind of a interesting, tough problem, because what does it mean to be aligned to human values? Which human? If you are aligned with Trump's values, do you consider that to be a good alignment? Well, there are people like me who might disagree that yes, that's the perfect alignment, right, that you want. So there is so much of even disagreement among humans. How do you even figure out, right, how the right kind of alignment should work and so on? So these are very interesting and open problems, I would say, and very important areas of research, because as these AI models are used to tackle problems that will impact lives, human lives, we want these models to do things to at least uh, give their output, right, in a responsible manner.
Let's thank.
Thank you. Thanks. Hi.
You
Yeah.
talked about how you're fine-tuning the like language models to India. So are you doing something similar? Is Google Research India doing something similar for weather forecasting and anything else that like Forecastcast, News, BCM, and all these models that they have?
Yeah, a team in India is not working on
Oh,
those
Like
weather
not
models.
making it better for India. That's not.
No, not at
Okay,
this
it's
point.
only for language and
Yeah,
all.
yeah, yeah.
Are you working on computational social science in media?
Uh, Not right now. There are, I mean, a lot of other people, researchers in India working in that area. Yeah, we don't have.
People who will implement engineers, plus so that 5 people.
Like one thing I really noticed is what is the future of like generating images or generating video? Like